This presentation is delivered by the Stanford Center for Professional Development.
Hey, well, welcome. We got a couple parents who have braved the other activities of Parents Weekend to come here, so thank you for coming to see what it is that we do here in CS106B. We are still in the process of grading the midterm. In fact, most of our grading we're planning on taking care of Sunday, in some big, massive grading session. So with any luck, if it all goes well, we'll actually have them ready to go back on Monday. But if somehow it turns into some disaster, it may take us a little longer, but hopefully that's the plan. So I'm going to finish up a couple slides from last time, and then I'm going to mostly go on to do some code with you together. But I just wanted to try to give you some perspective on the value of abstraction and the idea of an abstract data type or an ADT, and why this is such a powerful and important concept in management of complexity. So we saw this, for example, in those first couple assignments, right, that the client uses classes as an abstraction. You have the need to manage something that has a queue-like behavior, first in, first out. So what you want is something that you can put things in that will enforce that, put things at the end of the line, always return the head of the line, and that how it managed what it did and what went on behind the scenes wasn't something we had to worry about or even concern ourselves with. And in fact, even if we wanted to, right, we couldn't muck around in there. Like, it wasn't our business. It was maintained privately. And that is a real advantage for both sides, right, that the client doesn't have to worry about it and can't even get in the way of us, that we can work independently and get our things done. And so one sort of piece of terminology we often use here, we talk about this wall of abstraction, that there is kind of a real block that prevents the two of us from interfering with each other's process as part of combining to build a program together. And there's a little tiny chink in that wall, right, that we call the interface, and that's the way that you speak to the stack and ask it to do things on your behalf, and it listens to your request and performs them. And so if you think about the lexicon class, right, which we used in the Boggle and in the recursion assignment, right, that managed a word list, the abstraction, right, is, you say, is this word in there? Add this word to it. Load the words from a file. How does it store them? How does it do stuff? Did anybody go open up the lexicon.cpp file just to see? Anybody who was curious? What did you find out?
Actually, I think I ended up in there because I threw it there.
you ended up in there, and when you got in there, what did you decide to do? Leave. Yeah, did anybody else open it up and have the same sort of reaction over here? What did you think?
Yeah, I didn't really understand.
Yeah, what did you think?
It was a mess.
It was a mess. Who wrote that code? My God, she should be fired. It's scary. It does something kind of scary. We'll talk about it actually at the end. We'll come back to it because I think it's actually a really neat class to study. But in fact, like, you open it up and you're like, I don't want to be here. I want to use a word list. Let me close this file and let me go back to word list. Add word, contains word. Okay. And you're happy about that, right? It does something very complex that turns out to be very efficient and optimized for the task at hand. But back to Boggle, you don't want to be worrying about that. You got other things on your plate, and that's a fine place to just poke your nose right back out of. So if you haven't had a chance, go look at it, because we will talk about it later. But the person who wrote it, was a crummy commoner. I'm just saying that they would definitely not be getting a check plus on style. So I drew this little picture. It's like this wall, right? So when you made a lexicon, you say, oh, I want a lexicon. Add this word, add that word. Does it contain this word? And that there is this big wall, and you can think of what's on the inside as a black box. The black box is the microwave, right, that you push buttons and food gets hot. How does it really work? Who knows? You don't open up the back, you don't dig around in it. And this little chink here, right, that's the interface. And lexicon provides a very small interface, if you remember, adding the words, checking contains word and prefix, right, reading the words from a file, really not much else beyond that. And then now what we're starting to think about is like, well, what's this other side look like? What goes on over here? Is that there is this implementer, right, who does know the internal structure, who does know what shenanigans are being pulled on that inside, who does have access to that private data, and who, upon request, when you ask it to add a word or look up a word or look up a prefix, internally trolls through that private information and returns information back to the client, having mucked around in those internals. So when you say add a word, maybe what it's got is some array with a count of how many words are used, and it sticks it in the next slot of the array and updates its counter. We don't know what it does, but it's not really our business as the client, but the implementer, right, has kind of the full picture of that. And then over here on this side, if the client attempts to do the kind of things that are really implementer specific, it tries to access directly the num words and the words array to go in and say, yeah, I'd like to put pig in the array. How about I do this, right? How about I change the number of words? Or how about I stick it in the slot at the beginning and overwrite whatever is there? That an attempt to do this, right, should fail. Right? Should not compile because these fields that are part of the lexicon should have been declared private to begin with, to make sure that that wall is maintained. Everything that's private is like over here on this side of the wall, inaccessible right outside of that. And so why do we think this is important? Of all the ideas that come away from 106B, I think this is one of the top 3, right, is this idea of abstraction, right? We actually even call the whole class programming abstractions because that the advantage, right, of using this as a strategy for solving and larger and more complicated problems, right, is that you can divide up your tasks, that you can say this is an abstraction like a word list and kind of have it be as fancy as it needs to be behind the scenes, but very easy to use from the outside. So that makes it easy for me to write some piece and give it to you in a form that's easy for you to incorporate. We can work on our things without stepping on each other. As you get to larger and larger projects beyond this class, right, you'll need ways of making it so 3 people can work together without stepping on each other's toes the whole time. And classes provide a really good way of managing those boundaries to keep each other out of each other's hair. And there's a lot of flexibility that's given to us by this. And we're going to see this actually as we go forward, that we can talk about what a vector is. It keeps things in index order, or a stack is. It does LIFO. But there is no guarantee there about how it internally is implemented, no guarantee expressed or implied. And that actually gives you a lot of flexibility as the implementer. You can decide to do it one way today, and if upon later learning about some other new technique or some way to save memory or time, you can swap it out, replace an implementation with something better, and all the code that depends on it, right, shouldn't require any changes. That suddenly AdWord just runs twice as fast or 10 times as fast would be something everybody could appreciate without having to do anything in their own code to take advantage of that. So these are good things to know. So what I'm going to do actually today is I'm going to just stop doing slides because I'm sick of doing slides. We do way too many slides. I'm bored with slides. And what I'm going to do is I'm going to actually go through the process of developing vector from just the ground up. So my plan here is to say our goal is to make the vector abstraction real. So to get dirty, get behind the scenes and say, we know what vector is. It acts like an array. It has these indexed slots. It's this, linear collection. It lets you put things anywhere you like in the vector. We're going to go through the process of making that whole thing. And I'm going to start with a simple form that actually is not templatized, and then I'm going to change it to one that is templatized. So we're going to see kind of the whole process from start to end. So all I have are empty files right now. I have myvector.h and myvector.cpp that really have sort of nothing other than sort of boilerplate stuff in them. So let me look at myvector.h to start with. So I'm going to call this class myvector so that it doesn't confuse with the existing vector class, so that we have that name there. And I'm going to start by just putting in the simple parts of the interface, and then we'll see how many other things we have time to kind of add into it. But I'm going to get the kind of basic skeletal functions down and show how they get implemented, and then we'll see what else we'll try. So having the size is probably pretty important, being able to say, well, how many things have I put in there? Get that back out. Being able to add an element. And I'm going to assume that right now the vector is going to hold just strings. Certainly that's not what we're going to want in the long run, but I'm just going to pick something for now so that we have something to practice with. And then I'm going to have the get at, which, given an index, will return something. Okay, so I think these are the only ones I'm going to have in the first version. And then the other ones, you remember, there's like a remove at, there's an insert at, there's a overloaded bracket operator, things like that I'm not going to show right away. Question? Oh, yeah. This is actually, kind of just standard boilerplate for C or C++ header files, and you'll see this again and again and again. I should really have pointed this out at some point along the way, is that the compiler does not like to see 2 definitions of the same thing ever. Even if those definitions exactly match, it just gets its total, knickers in a twist about having seen a class myvector and another class myvector. And so if you include the header file myvector one place and you include it some other place, it's going to end up thinking there's 2 myvectors classes out there, and it's going to have a problem. So this little bit of boilerplate is to tell the compiler, if you haven't already seen this header, now's the time to go in there. So this if-end-def says if not defined, and then the name there is something I made up, some symbol name that's unique to this file. Then I say define that symbol. So that's like saying I've seen it. And then down here at the very bottom there's an end-if that matches it. And so in the case where we have, this is the first time we've seen the file, it'll say, if not define the symbol, it's not. It'll say, define that symbol, see all this stuff, and then the end-f. The second time it gets here, it'll say, if not define that symbol, say that symbol's already defined, so it'll skip down to the end-f, and so every subsequent attempt to look at my vector will be passed over. If you don't have it, you'll get a lot of errors about I've seen this thing before, and it looks like the one I saw before, but I don't like it. Smells suspicious to me. So that is sort of standard boilerplate for any header file, is to have this multiple include protection on it. Anything else you want to ask about the way in the back?
Why would it look at it multiple times, though?
Well, because sometimes you include it in something else. For example, think about genlib. Like, I might include genlib, but then I include something else that includes genlib. So there's these ways that you can accidentally get it in there more than once, right? Just because some other things depend on it, and the next thing you know. So it's better to just have the header file never complain about that, never let that happen, than to make it somebody else's responsibility to make sure it never happened through the includes. So I've got 5 member functions here that I'm going to have to implement. And now I need to think about what the private data this guy's going to look like. So now we are the low-level implementer. We're not building on anything else right now because my vector is kind of the bottommost piece of things here. We've got nothing out there except for the raw array to do the job for us. So typically the most compatible mechanism to map something like vector onto is the array. It does contiguous memory. It allows you to do direct access to things by index. And so that's where we're going to start. And we'll come back and talk about that, whether that's the only option we have here. But what I'm going to put in here is a pointer to a string, or in this case, it's going to be a pointer to a string array. So in C++, those both look the same. This says ARR is a single pointer that points to a string in memory, which in our situation is actually going to be a whole sequence of strings in memory, kind of one after another. The array has no knowledge of its length, so we're going to build it using new and things like that. It will not know how big it is. It will be our job, right, to manually track that. So I'm going to go ahead and have 2 fields to go with it, and I'm going to show you why I have 2 in a minute. But instead of having just a single length field that says the array is this long, I'm actually going to track 2 integers on it. Because likely the thing I'm going to do with the array is I'm going to allocate it to a certain size and then kind of fill it up. And then when it gets totally filled, then I'm going to do a process of resizing it and enlarging it. And so at any given point, right, there may be a little bit of excess capacity, a little slack in the system. So we might start by making it 10 long and then fill it up. And then as we get to size 10, make it 20 or something like that. So at any given point, we'll need to know 2 things about that array. How many of the slots are actually in use? So that'll be the first 5 slots are in use. And then the number of allocated will tell me how many total slots do I have? So how many slots can I use before I will have run out of space? Both of those. Okay. So there's my interface. So these things all public because anybody can use them. These things private because they're going to be part of my implementation. I don't want anybody messing with those or directly accessing them at all. So I put them down there. All right, now I go to myvector.cpp. So it includes myvector.h so that it already has seen the class interface, so it knows what we're talking about when we start trying to implement methods on the myvector class. And I'm going to start with myvector's constructor. And the goal of the constructor will be to set up the instance variables of this object into a state that makes sense. So what I'm going to choose to do is allocate my array to some size. I'm going to pick 10. So I'm going to say I want space for 10 strings. I want to record that I made space for 10 strings, so I know that the num allocated, the size of my array right now is 10, and the number used is 0. So that means that when someone makes a call, like a declaration that says my vector v, so if I'm back over here in my main, say my vector v, that the process of constructing that vector v will cause the constructor to get called, will cause a 10-member string element array to get allocated out in the heap that's pointed to by ARR, and then it will set those 2 integers to know that there's 10 of them and 0 of them are used. So just to kind of all as part of the machinery of declaring, right, the constructor is just wired into that so we get set up, ready to go with some empty space set aside. So to go with that, I'm going to go ahead and add the destructor right alongside of it, which is I need to be in charge of cleaning up my dynamic allocation. I allocated that with the new bracket, right? The new that allocates out in the heap that uses the bracket form has a matching delete bracket that says delete a whole array's worth of data, so not just one string out there, but a whole sequence of them. We don't have to tell it the size. It actually does. As much as I said it doesn't know its size, well, somewhere in the internals it does know the size, right? But it never exposes it to us. So in fact, when I say delete bracket array, it knows how much space is there to clean up. Yeah.
Are we just temporarily setting it up so that vector only works on strings?
Yes, we are.
Okay.
Yes, we're going to come back and fix that, but I think it's easier maybe to see it one time on a fixed type and then say, well, what happens when you go to template? What things change? And we'll see all the places that we have to make modifications. So I have my vector size. Which variable is the one that tells us about size? I got num used, I got num allocated. Which is the right one? Num used. That is exactly right. So num allocated turns out to be something we only will use internally. That's not going to. No one's going to see that or know about it, but it is. The num used tracks how many elements have actually been put in there. Then I write my vector add. Okay. So I'm going to write one line of code, then I'm going to come back and think about it for a second. I could say ARR num used plus plus equals s. So tight little line. It has a lot of stuff wrapped up in it. Using the brackets right on the dynamic array here, saying take the array and write to the num used slot, post incrementing it, so as a side effect. So if num used is 0 to start with, right, this has the effect of saying array of, and then the num used plus plus returns the value before incrementing, so that it evaluates to 0. But as a side effect, the next use of num use will now be 1. So that's exactly what we want. We want to write to the slot 0 and then have num use be 1 in subsequent usage. And then we assign that to be s, so that we'll put it in the right slot of the array. So once num used is 5, right, so that means the 0 through 4 slots are used. It'll write to the 5th slot and then up the num used to be 6, so we'll know our size is now up by 1. What else does add need to do? Is it good?
We need to make sure we have that many.
It better make sure we have some space. So I'm going to do this right now. I'm going to say if num used is equal to num allocated, I'm going to raise an error. I'm going to come back to this, but I'm going to say for this first pass, we're going to make it so it just doesn't grow. It picked some arbitrary size, it got that big, and then it ran out of space. Question?
So when the for the vector 0, the first time it gets called, it's actually going to be placed in index 1 of the array?
So it's placed in index 0. So num used plus plus, any variable plus plus, returns it evaluates to the value before it increments, and then as a side effect, kind of in the next step, right, it will update the value. So there is a difference between the plus plus num used and the num plus plus form. Sometimes it's a little bit of an obscure detail we don't spend a lot of time on, but plus plus num says first increment it and then tell me what the newly incremented value is. Num plus plus says tell me what the value is right now, and then as a side effect increment it for later use.
So the num use gets changed in that?
It does get changed in that expression, but the expression happens to evaluate to the value before it did that change. Question?
And is it really necessary to have the my vector double colon, or
Oh
is there
yeah,
any way for the
yeah.
function to
So
know
if I take this out, right, and I could show you what happens if I do this, is what the compiler is going to think that is it thinks, oh, there's just a function called size that takes the arguments and returns an int, and it doesn't exist in any context. It's just a global function. And then when I try to compile it, if I go ahead and do it, it's going to say num used. What's num used? Right? Where did num used come from? So if I click on this, it'll say, yeah, num used was not declared in the scope. It has no idea where that came from. So there is no mechanism in C++ to identify this as being a member function other than scoping it with the right names. You say this is the size function that is part of the myVector class, and now it has the right context to interpret that in and knows that when you talk about num used, oh, there's a private data member that matches that. That must be the receiver's num used. So one other member function we got to go, which is the one that returns string. And if I do this, it almost, but not quite, looks like what I wanted. So I say return array subindex. They said get at an index. I returned the string that was at that index. Is there anything else I might want to do here?
Check and see if the index is valid.
Yeah, why don't we check and see if that index is valid? Now, this is one of those cases where it's like you could just sort of take the stance that says, well, it's not my job. If you ask me to get, something at index 25 and there are only 4 of them, that's your own fault, and you deserve what you get. And that is certainly the way a lot of professional libraries work, because if I add in a step here that does a check, it means that every check, right, costs a little bit more, right? When you go in to get something out of the vector, it's going to have to look and make sure you were doing it correctly. And there are people who believe that if it's like riding a motorcycle without a helmet, that's your own choice. We're going to actually bulletproof, right? We're going to make sure that the index isn't whack. And I'm going to go ahead and use my own size there. I'm going to say if the index is less than 0 or it's greater than or equal to, and I'm going to use size. I could have used num_use there, but there often are reasons that if I use my own member functions and then later somehow I change that name or I change how I calculate the size, let's say I change it to where I use a linked list instead of an array and I'm managing the size differently, that if I have used size in this context, right, it will just change along with that because it's actually depending on the other part of the interface that I'll update. And so I'm going to go ahead and do that rather than directly accessing my variable. Say if that happens, I say error out of bounds. Other than that, right, that error will cause the program to halt right then and there, so I don't have to worry about it at that point getting down to the return. So I feel okay about this. Not too much code, right, to get kind of a little bit of something up and running here. Let's go over and write something that tests. Okay, so I put some things in there, and I'm going to see if it'll let me get them back out. So before I get any further, I might as well test the code I have, right? This is one of the things about designing a class, right, is it's pretty hard to write any one piece and test it by itself, because often there's a relationship, the constructor, and then some adding, and then some getting stuff back out. So it's a little bit more code than I typically would like to write and not have a chance to test, having all 5 of these member functions kind of at first. So if I run this test and it doesn't work, it's like, well, which part was wrong? Was the constructor wrong? Was the add wrong? Was the size wrong? You know, there's a bunch of places to look, but it's unfortunately they're kind of all interrelated in a way that makes it a little hard to have them independently worked out. But then each subsequent thing, hopefully I can add like the insert at method without having to add a lot more before I test. Okay, so I run this guy and it says Jason, Ilya, Nathan. I feel good. I feel good. I feel smart. I put them in that order. Seem to get them out in that order. Why don't I try some things that I'm hoping will cause my thing to blow up? Why don't I get at 10? To see. I'd like to be sure. I say, okay, why don't you tell me what's at the 10th slot in that vector? And it says, oh, out of bounds, just like I was hoping for. Oh, I like to see that, right? What happens if I put in enough strings that I run out of memory? We talked about the thing it's actually set to be 10 right now. Why don't I just make it smaller? That way it'll make it even easier for me. So I say, oh, how about this? I'm only going to make space for 2 things. Error out of space, right? That happened before it got to printing anything. It tried to add the first one, it added the second one, then it went to add that third one, right? It said, oh, okay, we've run out of space. We only had space for 2 set aside. You asked me to put a third in, I had no room. So at least the kind of simple behaviors that I put in here seem to kind of show evidence that we've got a little part of this up and running. What I'm going to fix first is this out of space thing. So it would be pretty bogus and pretty unusual for a collection class like this to have some sort of fixed limit, right? It wouldn't, it'd be very unuseful to say, well, it's always going to hold exactly 10 things or 100 things or even 1,000 things, right? One way you might design it is you could imagine adding an argument to the constructor that said, well, how many things you plan on putting in there, and then I'll allocate it to that, and then when we run out of space, you're host. But certainly a better strategy that kind of solves more general case problems would be like, well, let's grow. When we run out of space, let's make some more space. Okay, let's think about what it takes to make more space in using pointers. So what a vector really looks like is it has 3 fields: the ARR, the num used, and the num allocated. When I declare one, right, the way it's being set up right now, it's over here and it's allocating space for some number, let's say it's 10 again, and then marking it as 0. That as it fills these things up, it puts strings in each of these slots, and it starts updating this number. Eventually it gets to where all of them are filled, right? That when num used equals num allocated, it means that however much space I set aside, every one of those slots is now in use. So when that happens, it's going to be time to make a bigger array. There is not a mechanism in C++ that says take my array and just make it bigger where it is. That the way we'll have to do this is we'll have to make a bigger array, copy over what we have, and then have added on by making a bigger array full of space. So what we'll do is we'll make something that's like twice as big. I'm just going to draw it this way because I'm running out of board space. And it's got 10 slots and then maybe 10 more, and then I will copy over all these guys that I have. Up to the end, and then I have these new spaces at the end, and so I will Have to reset my pointer to point to there. Update my num allocated, let's say, to be twice as big or something, and then delete this old region that I'm no longer using. So we're going to see an allocate, a copy, a delete, and then kind of resetting our fields to know what we just did. So I'm going to make a private helper to do all this. And I'll just call that enlarge capacity here. Question?
Is this like costly process?
Well, it can be, is the truth. So you're getting a little bit ahead of us, but in the sense that, like, if the array has 1,000 elements, right, and now we've got to put that 1,001st thing in, right, it's going to take all 1,000 and copy them over, right, and enlarge the space. So in effect, what is typically an O of 1 operation, just tacking something on the end, every now and then, right, is going to take a whole hit of an end operation when it does the copy. But one way to think about that is every now and then it's really expensive, but kind of if you think of it across the whole space, that you got, let's say you started at 1,000, right, and then you doubled to 2,000, that the first 1,000 never paid that cost, and then all of a sudden one of them paid it, but then now you don't pay it again for another 1,000, that if you kind of divided that cost, sort of amortized it across all those ads, that it didn't change the overall constant running time. So you kind of think of it maybe in the big picture. It does mean every now and then, though, one of them is going to surprise you with how slow it is, but hopefully that's few and far between if we've chosen our allocation strategy well. So I'm going to say, actually I'm going to do this, I'm going to call this thing actually double capacity. So one strategy that often is used is you could grow in little chunks. You could grow like 10 at a time all the time. But if the array is going to get very big, going by tens will take you a lot of times. You might sort of use, in some sense, the indication of, well, how big is it already? Then if that's about the size it seems to be, why don't we go ahead and just double? So if we start at 10, and then we go to 20, then we go to 40, then we go to 80. Then as we get to bigger sizes, we'll make the kind of assumption that, well, given how big it is already, wouldn't surprise us if it got a lot bigger. So let's just go ahead and allocate twice what we have as a way of kind of predicting that it's pretty big now. It might get even bigger in the future. That isn't necessarily the only strategy we could use, but it's one that actually often makes pretty decent sense. And then at any given point, you'll know that the vector will be somewhere between full and half capacity is what you're setting up for. So let's do this. Oops, it's not ints. String bigger equals, and I make a new string array that is num allocated times 2. So twice as big as the one we have. And now I go through and I copy. So copying from my old array to my bigger one. All of num used. In this case, num used and num allocated are exactly the same thing. And then I'm going to reset my fields as needed. I'm going to delete my old array because I'm now done with it. I'm going to set my pointer to this, right? So that's doing pointer assignment only, right? So I deleted the old space. I've copied everything I needed out of it. I'm now resetting my pointer to the bigger one, and then I'm setting my num allocated to be twice as big. Num used doesn't change. Okay, so went through the process of building all these things, and as noted, right, that is going to cost us, right, something linear in the number of elements that we currently have. So this guy is intended to be a private method. I don't want people outside of the vector being able to call this, so I'm actually going to list this in the private section. It's not as common that you'll see member functions listed down here, but in this case, it's appropriate for something that you plan to use internally as a helper, but you don't want anybody outside to just be calling double capacity when they feel like it. Question?
So normally, there's an array, so you couldn't actually declare its size like that, though, right, with a variable?
I don't understand the question. Try that again.
So, in this case, to enlarge it, you use a variable for the size of the array. But when you normally declare an array, you couldn't do that, right?
Well, if you did it,
it has to be a constant.
So like if you use this form of an array, where you declared it like this, did you see what I just did?
Yeah.
Yeah, that way won't work, right? That way is fixed size, nothing you can do about it. So I'm using totally the dynamic array at all times, right? So that the dynamic array.
So you can do that when you're declaring it on a heap.
Yes.
Okay.
Yes, exactly. So all I have stored in the vector itself is a pointer to an array elsewhere, and that array in the heap gives me the flexibility to make it as big as I want, as small as I want, to change its size, to change where it points to, You know, all the dynamic arrays typically just give you a lot more flexibility than the static
So
array.
that's really a stack heap.
That is very much a stack heap thing. When
Okay.
you put on the stack, you have to say how big it is at compile time, and you can't change it. The heap lets you say, I need it bigger, I need it smaller, I need to move it in a way that the stack just doesn't give you that at all. So then I go back to my vector.cpp. The place I want to put in my double capacity here is when num used is equal to num allocated. That what I want to do is call double capacity there. After I've done that, right, num allocated should have gone up by a factor of 2. Space will be there at that point, right? I know that num used is a fine slot to now use to assign that next thing. So whenever we're out of space, we make some more space. And so I'm going to, right now I think my allocated is still set at 2. That's a fine place. I'd like it to be kind of small because I'd like to test kind of the some of the initial allocations. So I'll go ahead and a couple more people, so I can see that I know that at that point, if I've gotten to 5, I'm going to have doubled once and then again, right, to get there. And I'll take out my error case here. See that I've managed to allocate and move stuff around. Got my 5 names back out without running into some craziness. So that makes me feel good about what I've got going there. So I could go on to show you what insert and remove do. I think I'm probably going to skip that because I'd rather talk about the template thing, but I could just tell you, like, a sketch the implementation. What does insert at do? What does remove at do? Basically, right, they're doing the array shuffling for you. If you say insert at some position, that has to move everything down by 1 and then put it in there, whereas add is actually just tacking it onto the end of the existing ones, right? The insert and remove have to do the shuffle to either close up the space or open up a space. They'll probably both need to look at the capacity as well. If you're inserting in your already capacity, you better double before you start. And then the remove at also may actually want to have a shrink capacity, where when we realize we previously were allocated much larger and we've gotten a lot smaller, should we take away some of that space? A lot of times the implementations don't bother with that case. They figured, if it's already allocated, just keep it around. Right, you might need it again later. So it may be that actually we just leave it over allocated even when we've deleted a lot of elements. But if we were being tidy, right, we could take an effort there. What I want to do is switch it to a template. So if you have any questions about the code I have right here, now would be a really good time to ask before I start mucking it up. Way in the back. I will. You know, that's a really good idea, because at this point I want to start to change it, and then it's going to be something else before we're all done. So let me take a snapshot of what we have here, so that before I destroy it. Question.
And when is the constructor get called?
Okay. So the destructor gets called in the most. There are 2 cases it gets called. One is when the constructor gets called when you declare it, right? And then the destructor gets called when it goes out of scope. So at the opening brace of the block where you declared it in, right, is when the constructor is happening, and then when you leave that. So in the case of this program, it's just at the end of main. But if it were in some called function or in the body of a for loop or something, it would get called when you enter the loop, and then called as destroyed as it left. For things that were allocated out of the heap, so if I had a myVector, new myVector, it would be explicitly when I called delete that thing when I was done with it. So it's basically when the variable that holds it is going away, right? Either because you're deleting it out of the heap or because it's going out of scope on the stack. Here.
When you have string star array, or ARR, it's a pointer to a single string, and then later you can use a new statement to link it to an array. So how does it know when it's...
How does it know? It doesn't, is the truth. Is that when you say something's a pointer to a string, the only guarantee is really there. It says it's an address of some place where a string lives in memory. Whether there's one string there or a whole sequence of strings is something you decide and you maintain. And so the compiler doesn't distinguish those 2 cases. It does not know that you made exactly one string at the other end of this or 500. And so that's why this idea of tracking the number used and allocated becomes our job, that they look exactly the same in terms of how it interprets them. It says, well, it's the address of where a string lives in memory, or maybe it's a sequence, I don't know. And so it lets you use the brackets and the new and stuff on a pointer without distinguishing, having any mechanism in the language to say this is a single pointer and this is an array pointer. They look the same.
So you could use the bracket notation on a single pointer?
You certainly can. It's not a good idea, right? But you can do it, right? So it legally in the language, right? It just makes no distinction between those, right? They are really commingled in a way that's one of the more surprising features of C and C++, and one that's a little bit hard to get your head around, is that it doesn't track that it's a pointer to a single thing versus a pointer to an array. That they're both just pointers in its mind, and that allows opportunity for errors when you mistreat them as the other type, for example. Question.
Can you go over in your CPP file at the end with the for loop. What's going on with the pointers real quick? Because it's just...
Yeah. So let me. It's basically the thing that I drew over here, but I'll do it again just to watch it. Right? Is that let's imagine I have a slightly smaller num allocated, so it's a little less gunk for me to write. So let's say that I'm going to use a num allocated of 2. Right? So it allocates 2. So when I construct it, it makes a block that holds 2 things, and the num used is 0. So I do 2 adds. I add A. It increments num used to 1. I add B, it increments num used to 2. I try to add C. It says, oh, well, num used equals num allocated. We're going to go to double capacity now. So double capacity has this little local variable called bigger. And it says bigger is going to be something that is 4 strings worth in an array. So it gets 4 out there. It does a for loop to copy the contents of the old array on top of the initial part of this array. So it copies over the A and the B into there. And then it says, okay, I'm done with this old part, so let me go ahead and delete that. And then it resets the ARR to point to this new one down here where bigger was. So now we got 2 aliases at the same location. And then it sets my num allocated to say, and now what you've got there is something that holds 4 slots. And then that used call here says, okay, and now write the C into the slot at 3. So the process here is the only way to enlarge an array in C++ is to make a bigger one, copy what you had, and then by virtue of you having made a bigger array to start with, you have some more slack that you didn't have before. Daniel?
Why doesn't delete ARR with a star?
It has to do with just delete takes a pointer. It doesn't. So a star ARR is a string, right? ARR is a pointer to a string. So both forms of delete, the delete and delete bracket want the
Conceptually,
pointer.
there is a star there because it's delete.
Well, effectively, yeah, it's delete the thing at the other end of the pointer, really. But it's funny. Delete says take this address and reclaim its contents, right? And so it doesn't really operate on a string per se. It operates on the storage where that string is. And so I don't know whether you want to call that is there an implicit star there or not. It really is about the pointer though, rather than the contents. So it's like that address has some memory associated with it. Reclaim that memory.
With arrays,
Uh-huh.
so when you're first declaring, or when you're making the pointer like string bigger, string star bigger, you have to declare it with the star notation, but then later on you don't ever have to use that again?
You pretty much won't see that star used again, right? It's interesting that things like bigger sub I and array sub I implicitly have a dereference in them, and that can be misleading. You think, well, how come I'm never actually using the star again on that thing to get back to the strings that are out there? And it has to do with the fact that the bracket notation kind of implicitly dereferences in it. If I did a star bigger, it would actually have the effect of giving me bigger sub-0, it turns out. You can use that notation, but it's not that common to need to.
And so down the last one line up from the bottom, it says array equals bigger. You don't have to...
Yeah, if you did that, if I did say...
If you said array...
Star ARR equals star bigger, I would not be getting what I want. Right? What it would be doing is it would say, follow bigger and see what's at the other end. So that would follow bigger and get that string A. And then it would say follow ARR and overwrite it with that A. So it would actually have the effect of kind of only copying the first string from bigger on top of the first string of array. But array would still point to where it was, bigger would still point to where it was, and we would have not have updated the pointer we really wanted to point to the new array. So there is a difference, right? Without the star, we're talking about changing the pointers around. With the star, we're talking about the strings at the other end. And so this is a string assignment. It says assign one string to another. Without the stars on it, it's like assign one pointer to another. Make 2 pointers point to the same place. When you're done with this, right, bigger and ARR will be aliases for the same location. That's a very important question, though, to get kind of what that star is doing for you.
After ARR equals bigger, can you delete bigger after that?
If I deleted bigger, at that point, right, ARR is pointing to the same place. And so remember that having 2 or 3 or 10 pointers all at the same place, if you delete one of them, they actually effectively are all deleted, right? The delete really deletes the storage out here. And then if I did that, it would cause ARR to then be pointing to this deleted piece of memory. And not a good scene will come from that, right? It means that when it later goes back in there and starts trying to read and write to that contents, right, at any moment it can kind of shift underneath you, right? You don't own it anymore. It's not reserved for your use. So if we did that, we'd get ourselves into trouble, right? So there should basically be a one-to-one correspondence between things you knew and things you delete, right? And so in the my vector case, right, we knew something in the constructor that we're going to delete in the destructor. If at some point along the way, right, we got rid of our old one and got a new one, right, that's the new one that's going to get deleted. If we deleted it midstream here, right, we would just be asking for havoc when we start accessing that deleted memory. Way in the back.
Is it possible to create a pointer to something, a pointer to the address that's one off the end of the original array, and then just create an array just off the end there?
Not really. So new doesn't let you decide where you want something, right? So your point being saying, well, I can tell you what this address is. Can I just make space right there, and then I won't have to copy? And it turns out new just doesn't give you that kind of control. You ask it for space, it finds it wherever it has, and you can't. There isn't even a mechanism where you could suggest where you'd like it to be. You could say, well, that piece right there would be really handy. Could you please give me that one? It just doesn't give it to you. So you're really. This is the way that typically you have to manage a dynamic array. And this is actually one of the big drawbacks to the contiguous memory, right, as a mechanism for implementing things, right, is that fact that it has to maintain contiguousness means you have to shuffle and move and copy this block without the flexibility of something like a linked list where every cell is independently manipulated. In the back.
What happens if we replace the delete brackets ARR as delete just ARR?
So the difference is that if you allocated something with new string bracket, new something bracket, you need a delete bracket. If you actually use delete without the brackets, it thinks there's a single pointer and there's only one string at the other end, where delete bracket says delete the whole gob of strings that are there. If you don't do it, the consequence is not that big. It's like some memory gets orphaned, some things don't happen, but to be totally correct, right, they go hand in hand. If you use new with no brackets, use delete with no brackets. If you use new with brackets, use delete with brackets. So it's either both with brackets or both without.
So even though ARR is just a point to the first place,
yeah,
brackets knows the...
Yeah, it does. And so that kind of makes me feel like I'm a liar, because I said, well, the array doesn't know its length. Well, it does somehow, right? Internally, right, it is maintaining some housekeeping, but it doesn't expose it to you. So when you say delete bracket ARR, it knows, oh, there's a bunch of strings there and I got to do a bunch of cleanup on them, but it doesn't ever expose that information back to you. It doesn't let you depend on it. So it's up to you to maintain that information redundantly with it. All right, let me see if I can make it a template. I probably can't do this actually fast enough to get it all done today, but we can at least get started on it. So then I introduce a template header, and I make up the name that I want here. So same class header now, other than type name elem type. Then I look through my interface and I see places where I previously had said it's strings, it's strings, it's storing strings, and I say it's not actually storing strings. It's going to store elem type things. It's going to return elem type things. And it's going to have an array of elem type things. Okay, so I think that's everything that happened to the interface. Let me see if I see any other places that I've... So the interface part is kind of small. There's one other change I'm going to have to make to it, but I'm going to come back to it. I'm going to look at the code on the other side for a second and say, okay, well, that wasn't so bad. Now, it turns out that it gets a little bit goopier over here, because that template type name has to go on every one of these. Introduce them with the template type name elem type, and now there's another place where it needs to show up. So the full syntax for this is now saying this is a template function depending on elem type, and it's actually for the myVector who is being we're writing the myVector constructor for something whose name is myVector angle bracket elem type. So there's going to be a lot of this goo. Every one of these is going to kind of change its form from just looking like the ordinary myVector class scope doesn't really exist anymore. myVector is now a template for which there's a lot of different class scopes, one for each kind of thing being stored. So myVector of int is different than myVector of string. So we say, well, if you were building the myVector constructor for myVector string, it looks like this, right? Or, having filled in elem type with those things. So everywhere I was using string, right, I'm going to chain to elem type in the body as well. And then I have to kind of take this guy and use it in a bunch of places. I'm going to use it here. And then I'm going to have to do it down here. On that side. Here. It's going to return something with elem type. Here. It's a little bit of a mess to do this, right? And the code definitely gets a little bit goopier as a result of this. It doesn't look quite as pretty as it did when it wasn't a template. But it becomes a lot more useful. Okay. So then I need to look for places that I used string, and every place where I was using string, assuming that's what I was storing, it now actually turns into elem type. So my My pointers and the kind of array I'm allocating is actually now made into element type. The rest of the code actually didn't say anything specific about what it's doing, just copying things from one array to another. And now, depending on what the arrays are, it's copying ints or strings or doubles. And then other places in the interface where I'm doing add or where I'm doing get at, right, I have to be describing the things that are coming in and out as element type so that they can be matched to whatever the client's using. The rest of it looks okay.
Why do you have to write template type name element type above every?
Because you just have to, because it's C++. Because the thing is, that piece of code is itself a template, right? So these are like little mini templates. So I had the interface which said, here's the template pattern for the interface, and each of these says, when you're ready to make the size member function for a vector of int, it comes off this template. So this template describes what the size member function looks like for any of the my vectors you might instantiate, and it's described as a template because, in fact, we need to build a new size for ints versus doubles versus strings. It's even funny because you think of my size, like, well, size doesn't even use anything related to the element type. But in fact, right, each of the member functions is kind of specific. It's not just a my vector size, it's the my vector int size, the my vector string size. And that for some of the member functions, it's quite obvious why you needed distinct copies. Get at, right, returns an int in some cases and a double in others. But even the ones that don't appear to have any dependence on the element type actually are separated into their own individual versions. So I think I got all of that fixed, and then I'm going to have to do one thing that's going to seem really quirky, and it is very quirky, but it is C++. Let me show you what I'm going to do. Is I'm going to take my vector out of the project. They stop compiling that, and I'm going to change how it is that my vector gets compiled by doing this. Okay. Take a deep breath. This is really just an oddity of C++. So the situation is this, that templates aren't really compiled ahead of time. Templates are just patterns. You know, they like describe a recipe for how you would build a myVector class. But you can't just compile myVector and be done with it, because until the client uses it, you don't know what kind of myVectors you're building. Are they myVectors of ints or strings or student structures? So it turns out that the myVector really needs to get compiled at the usage, at the instantiation. When you're ready to make a myVector of students, it then needs to see all the code for myVector so it can go build you a myVector for students kind of on the fly. In order to see that code, it actually has to be present in a different way than most code. Most code is compiled, it's in a .cpp, and it just gets compiled once and once for all, like the random library. Random integer doesn't change for anybody's usage. There's a random.cpp, it compiled the function, you're done. So the template code does not get compiled ahead of time. It doesn't get listed in the project. What happens is the .h typically has not only the interface, but actually all the code. And so the two ways to get the code in here, one way is I could have just put all the code down here, and that's the way a lot of professional code gets written. It has the interface followed by all the template code right after it. I like to keep us thinking about the interface and the implementation being separate, so I'm actually taking the interface and keeping it in the .h, keeping the implementation over here in a .cpp, and then I'm using the pound include mechanism in a very unusual way that almost never would you want to, in a regular usage, to pound include another .cpp file. For templates, we're making an exception, and we're saying, well, in this case, because I really need that code there, the pound include mechanism is basically saying, go take the contents of this thing and just dump it in here. It really is an include mechanism. It says, go get this file and take its text contents and dump it right into this file, so that when somebody's trying to import the myvector.h, they're getting both the interface plus all the code that will generate a pattern from. So this is definitely just a quirk. There's no consistency between how other languages that do stuff like this expect this, right? This is just unique to C++ and its compilation mechanisms that require this kind of sort of slight, variation in handling. So we'll see this for all the templates we'll use, is that they will not be included as normal CPP files. They will get included in the .h, and there is this exact pattern which is reproduced for every one of the ones in the text. You'll see it on stack and queue and vector. That becomes the kind of boilerplate we'll use when making a template. So in general, I'd say be very wary of anything that looks like this. This is not a normal thing to do, and we're doing it just specifically to kind of keep up the illusion that the interface and the implementation are kept separate, because there's actually some good thinking that comes from that. But the way the compiler sees it, right, it doesn't want them to be separate, and so we have to accommodate it with this little hack, let's say here. So once I've done that, I go back to lecture. If I change this to be myVector string, I'm hoping that everything will still work. which it did, kind of amazingly. Daniel.
So where does the myvector.cpv file
So it's actually just living in the same directory with this, the way myvector.h is. So typically, like your .h files are just sitting in the same directory. The .dpp is sitting in the same directory. That's where it's going to look for it when it goes pound including, is in the kind of local contents.
But like, where is that? Like, is that in resources?
No, it's just, if you look, this is the directory I have. This is the contents of my, all my files, my project file. This is where the thing gets dumped. It's just sitting right there with all the code. And then I should be able to change this now to put some numbers in and have it do both. I just did it with strings, and I'm going to do it with ints, and voila, right, we now have something that holds ints. And so certain amount of goo, right, that went from the simple form to the template form, but a lot of power gained, right? Suddenly we took this thing that was one purpose, right, that held strings only, and you just made it to where it can hold anything you can think of to stick in there by making little machinations in the syntax there. So we'll see a lot more of this. It's not the first nor the last syntax that for templates that we're going to be playing with, but that will be next week in the cafe with me if you got some time. Otherwise, I will see you on Monday.